1 2 3 1 2 3, right? So here's an interesting situation that I want to discuss with you on inclined planes. So we have an elevator which is moving up with an acceleration, call it a naught equal to g, say, right? And there is an inclined plane, as you can see here, of mass small m, everything smooth, angle theta and height of the inclined plane is h, and there is a particle of mass m at the top of the inclined plane, right? Now what we want to figure out is that, after all, you would imagine that this block will slide downwards. We want to figure out the time taken by the block to reach the bottom of the incline. We want to find the time taken by the block to reach the bottom of the, given that the inclined plane is free to move and this surface is smooth and that there is enough room. We want to be able to figure out the time taken by the particle A to reach the bottom of the plane, given that the inclined plane is free to move. So first of all, few things that you must know. If there is an inclined plane of mass capital M which is free to move on a horizontal surface, and there is a particle of mass small m, right, which moves with an acceleration small a with respect to the plane. Acceleration of the particle m with respect to the plane is small a along the plane. This is the relative acceleration of small m with respect to the inclined plane. The result that we've derived earlier, and it would be a good idea to remember, the inclined plane moves to the left with an acceleration capital A. Then capital A is given by mg sine theta cos theta by capital M plus small m sine square theta. And small a, the relative acceleration of small m with respect to the inclined plane, is like a capital M plus small m g sine theta by capital M plus small m sine square theta, right? This is what you want to know. The other thing that you would do good to realize is that if the lift is moving up with an acceleration a naught, then the whole system could be reduced to a system in which the lift is stationary, It's as if the lift is at rest, and this is h, this is theta. It's as if the lift is at rest, that means in the left frame of reference, and g gets revised. Then the g effective, the new g, is like a g plus a naught. That's the new g. The new g is going to be g effective equal to g plus a naught. A naught is the acceleration upwards. If the lift was moving down, then it could be equivalent to putting the lift to rest and replacing g by g minus a naught if it was moving down. Now, so what we are interested in is the acceleration of small a with respect to the inclined plane, where g is replaced by g plus a naught. If g is replaced by g plus a naught, then small a, the relative acceleration of small m with respect to the inclined plane, is given by capital M plus small m g sine theta divided by capital M plus small m sine square theta, right? So all that I need to do here is replace this g by g plus a naught in view of the fact that the lift has an upward acceleration a naught. So the a here can be obtained from the a here by simply replacing g by g plus a naught. So the a here in this situation is like a capital M plus small m. See, capital M in this case is equal to small m, so that makes it 2m in the given situation. The mass of the inclined plane is small m, the mass of this particle is also small m. So capital M is also small m, so that's like 2m, and g becomes like a g plus a naught sine theta divided by small m taken common because capital M is the same as small m into 1 plus sine square theta, right? So m is going to get cancelled, and a naught is given to be g. A naught is given to be g. So if a naught is g, this is going to become 2g. So this becomes like a 4g sine theta, 4g sine theta divided by 1 plus sine square theta. 1 plus sine square theta. That's the acceleration of capital A with respect to the inclined surface. Now, constant acceleration. So, in order to cover this length is how much? This length is h cosec theta. As you can see, this length is h cosec theta. Right? So, it needs to cover h cosec theta with an acceleration parallel to the plane with respect to the plane equal to small a given by this expression. Yes or no? So then, if t is the time taken, then h cosec theta is half of a, which is this 4g sine theta divided by 1 plus sine square theta into t squared. That's what happens, right? So let's simplify matters here. This is going to become 2g then, 2g, and then we have like a t squared equal to h into 1 plus sine square theta divided by 2g sine theta. 2g sine square theta. This is going to become sine square theta. So this is sine square theta. 2g sine square theta. So then t is very clearly root h into 1 plus sine square theta. Root h into 1 plus sine square theta divided by 2g sine square theta. That's the time taken. So realize, not a difficult problem, but it would have been a good idea to know some of these results. You want to know what happens to the acceleration of small m with respect to the inclined plane parallel to the plane, given that the plane is free to move, which is this result. 1, 2, you also want to know that if there is a lift moving up with an acceleration a naught, it's as if the lift is at rest, and g is replaced by g plus a naught. A naught is g, so this is going to become 2g. That's one thing. So we replace g by 2g. This is going to become 2m because capital M is the same as small m in this situation. So 4g sine theta, 4g sine, and so on and so forth. And then all that you need to do is h cosec theta is half of a into t squared. Right? All right, we'll catch you in some time. Bye.